Advanced Algebra, Chapter 6, Lesson 6, when we're going to wrap this up by giving you a 5-step procedure for determining all of the zeros of a polynomial. And then I'll do 3 examples towards the end of the video so you can see those. And we are going to change one thing that hopefully, well not hopefully, that should shorten up the process just a little bit moving forward. So let's take a look at that. Now, we can find all of the zeros of the polynomial using a combination of graphing, the factor theorem, polynomial division, remainder theorem, and quadratic formula. So basically what we can do is we can combine all the things that we've learned in this chapter to, first of all, give us a roadmap as to where we should end up, what kind of numbers we're looking for, and then we can use some of the things we've learned, synthetic division and graphing, those things to actually help us along the way. Now, if we take the time at the beginning of the problem to think through each of these theorems, to think through the algorithms and the formulas that we're going to need, we should be able to get an idea of what our answers should be before we get to the end and as we're doing it, so we kind of have an idea of whether we're doing things correctly along the road. So we just need to kind of slow down, take a moment to plan, to see what we're going to have to do, and then as we're going along the way, we're able to see if we start getting off the track, we know we need to stop and turn around and figure out where we went wrong. So basically, here's what we want to do. Step number 1, if I can get this, we want to begin by thinking about the fundamental theorem of algebra and its corollary, and first figure out, well, how many zeros should we have at the end? And remember, that equals the degree, so that's an application of that. We then want to apply the rational zeros theorem and make a list of the possible zeros. Now here's where I'm going to make a change. We've then, from that list, been using the remainder theorem, where we substitute these values into the expression to find out which one out of that list, if any, will give us a remainder of 0 and thus be factors of the polynomial. Sometimes we can have a pretty long list to go through, so we can shorten that up even further by using our graphing calculator. So in my examples that I give you at the end of this lesson, I'll be using the graphing calculator to show you how you can take that rational zeros list and make it smaller and not have to use the remainder theorem with every single one of those possible zeros. So I'll be doing that by using the graphing calculator. Once we have the zeros, just like we did with the remainder theorem, we then use those zeros to synthetically divide the polynomial, dividing us down to our quadratic, where then we use a method of solving the quadratic in order to find those last couple of zeros, whether it be using the quadratic formula or whether extracting the square root or completing the square. Any of those methods will help us determine those last couple of zeros. And then at the end, once we have our answers, we can go back to question 1 and look at our answers and see, do these answers make sense? Do I have as many zeros as I should have? Do I have the proper number of imaginary zeros or real zeros? Okay, so by beginning with answering those questions, taking these theorems and applying them in order, we can then go back at the end and check and see, does my answer make sense? And this is really something that we should do in every problem that we do after we've determined the answer. We should always take a moment to think about, well, does my answer make sense as to what I'm doing before we move on? Because sometimes we can catch errors that we've made just by going, well, wait a minute, that number just doesn't make any sense in the context of what I'm doing. So if we follow those steps, then we should be able to determine all of the zeros. So I'm going to walk you through this one step at a time, and then I have the answer here, and actually the book does this, and then we'll see how the book does it, and then again I'll walk you through 2 examples of that. So we are asked to find all of the zeros. So the first thing we want to do is get an idea of where we're going. Well, how many roots should we have at the end? Well, it's a degree 3, so I should have 3 roots when I get to the very end. Okay, so that kind of tells me where I should end up. I then want to begin my process by making a list of the possible zeros. Using the rational zeros theorems, taking the factors of the constant over the factors of the leading coefficient, my rational zeros are either going to be plus or minus 1 or plus or minus 2. So I can use the rational root theorem to do that. I'm then going to, in this case, we've been using the remainder theorem. We substitute 1 into the expression -1 to +2 and -2 in order to find out which one of these actually are zeros. Again, I'll show you how to use the calculator to do that. Once we've done that, though, we then take the zeros and use synthetic division to make sure that we get a remainder of 0. So, substituting -2 into the expression, I see that that should give me a remainder of 0. I then use that to use synthetic division. So, using synthetic division, I end up with this expression here. Now, if I put the variables back in, I have a quadratic, x squared minus x plus 1, giving me a remainder of 0. Now, this is a quadratic, so my next step is to then use what I know about quadratics to solve it for 0. Because I have a remainder of 0 here, I proved or confirmed that -2 is a 0. So, using the quadratic formula then, given this last quadratic, I'm then able to determine the last two zeros of 1/2 plus or minus I square root of 3 over 2. So that's two zeros. It's a half plus this and a half minus this. So how many zeros do I have? Well, I have the one real zero, rational zero, that I determined using synthetic division. And then I have these two, so I have 3, which is exactly how many I said I should have when I began the problem. So you can see by knowing how many we said we should have or getting an idea of that, we're then able to check our answer at the end to see if it makes sense. And it makes sense in terms of I have 1 real and 2 irrational. That makes sense. The irrationals, or imaginaries, come in pairs. Therefore, the 2 imaginary along with the 1 real makes sense for a total of 3. All right? So again, if we just follow these steps and keep those in mind, we should be able to find these zeros rather easy. Okay, I'm going to do 2 more examples, and I'm going to walk through these so you can watch that, and hopefully those will be helpful to you. So let's take a look at this example here where we're asked to determine all of the zeros. So we start by using the fundamental theorem of algebra and figure out or get an idea of how many zeros we should have when we get to the end. And because this is a degree 4, I should end up with 4 zeros at the end. Now, if I take a look at the possibles, possible real zeros, if I have 0 real, can I have 4 imaginary? Yes. So I could have none of them be real. That's a possibility. I can't have one real because that would leave 3. I could have 2 real and 2 imaginary, or I can have 4 real and none imaginary at the end. So it is possible for me to have any of these combinations of real zeros. I then want to use the rational zeros theorem to list my potential zeros, and we take the factors of the constant, which here is 8, over the factors of the leading coefficient is 1. So if I have rational zeros, it's either going to be plus or minus 1, plus or minus 2, plus or minus 4, or plus or minus 8. If I have rational zeros, it's going to come from this list. Now here's where we're going to make a slight change, where we have been using the remainder theorem to substitute these into the expression to find out which ones would give me a remainder of 0 and thus be zeros. In this case, we want to use the calculator. I'm going to show you how to use the calculator. So we take this expression and we substitute it, or we plug it into our calculator for y1, and here's the graph that we get. Now you remember the rational zeros are where the graph crosses or touches the x-axis. So I want to look at the graph here, and I can see that it crosses or touches at these points right here. I'm going to get a scale here where it's, let me go back to this. Okay, so I see that it crosses here about at -2 and +2. So I want to look, are -2 and +2 in my list? Okay, so if I look in my list, I see that -2 and +2 are my list. So it's possible that these could be zeros. All right. Now I notice in my graph that it does cross or touch in 2 other places, one here and one here. And you'll notice that's between 1 and 2. So those are fractional zeros. There's somewhere between 1 and 2. If I look in my list of potential zeros, I don't have any fractions. So that means while the graph crosses or touches here, those are not rational zeros. Therefore, they must be irrational zeros. And I can't figure those out doing anything here other than to know that there are some irrational zeros that I'm going to have at the end. So the only two zeros from my graph that appear to be zeros are these two numbers. So now we're going to use synthetic division to actually divide these out and confirm that these are zeros. Now I could use remainder theorem here and substitute these in and make sure they're zeros before I start, but if I'm going to synthetically divide anyways, it really doesn't matter. So we'll divide by -2 first. So I list my coefficients. So there's an x to the fourth, 0x cubed, -6x squared, 0x, and then an 8. And then we'll use my synthetic division. So we're going to multiply and add. We're going to multiply and add. We're going to multiply and add. And we're going to multiply and add. So I get a remainder of 0. So 2 is definitely one of my answers, or one of the roots of the expression. I'm then going to divide by 2. So I'm going to multiply and add, I'm going to multiply and add, and I'm going to multiply and add. So I now have confirmed that 2 is also a 0. So I have 2, but I'm not done because I see I'm supposed to have 4. So I have here a quadratic now because this was x to the fourth, this was x cubed, so now this is x squared plus 0x minus 2. So I have a quadratic. It does not have a linear term, so I can just set it equal to 0 and extract the square root. So 2, so this is going to be plus or minus the square root of 2. So I have two irrational zeros, a positive square root of 2 and a negative square root of 2. So my answer has 4 zeros, which I know I should have. I have 4 real answers, which is okay to have. My rational zeros came from my list, and so I have determined all of the zeros, and I can see that my answer makes sense as to what I thought I should get when I began the process. Okay, so again, we use those processes, and again, we're going to use our calculator to help us out here. Instead of the remainder theorem, you can still continue to use the remainder theorem, and that might be kind of easy if there's only a few numbers here, but if you get a long list of possible zeros, using your calculator to narrow that down will be a little bit quicker and easier. Alright, I'm going to do one more example for you in this video so you can check that out. So for our final example, we have 15x cubed minus x squared plus 3x minus 2. So I want to begin again by using the fundamental theorem of algebra, or the corollary, and figure out how many zeros I need to end up with. The degree is a 3, so I need to end up with 3 zeros. I then want to maybe take a quick look and see how many of these could be real zeros. Now, if I have 0 real, that means all 3 are complex. That's not possible. So I have to have 1 real at least. So 1 is real, 2 are imaginary, that's okay. Or all 3 of them could be real, because then I have 0 imaginary, and that's okay. I then am going to use the rational zeros theorem to make a list of my possible rationals. So I take my factors of my constant, which are 1 and 2, over the factors of my leading coefficient, 1, 3, 5, and 15, and I can make my list. So I'm going to have plus or minus 1, plus or minus 1 over 3, plus or minus 1 over 5, and plus or minus 1 over 15. Those are possibles. Plus or minus 2 over 1, plus or minus 2 over 3, plus or minus 2 over 5, and plus or minus 2 over 15. So these are my possible rational zeros. Now again, you can see this is quite a few to have to substitute in and to check how many of these are actually zeros. So I'm going to use my calculator. That will cut this list down much quicker. So if I graph this expression, here's the graph, and you'll notice it only crosses in one place, right here. So there's only going to be one real 0. The other two must be imaginary because it doesn't cross anywhere else. So I just have to figure out where this is. So this is somewhere between 0 and 1. So it's one of those fractions between 0 and 1. So if I go back here, it could be 1/3, 1/5, 1/15, 2/3, 2/5, 2/15. It could be any one of those. So that narrows them down a little bit. If I take a closer look at this, maybe zoom in a little, maybe I can get a better idea of what this might be. Let's see, is this helping? Let's see, let me try to do this in a way. Okay. All right, so this is 1. So I changed my window so that this is 1. So each one of these is 0.1. So this is 0.1, 0.2, 0.3, 0.4. So that'd be 4/10 or about 2/5. So looks like 2/5 is going to be my best guess as to what might be the 0 here. So I'm going to synthetically divide by 2/5 and confirm that that is my 0. So I list my coefficients, 15 squared, I don't need a plus sign there, x, and then -2. So 3, 2, 1, and then 0, and I'm going to do this multiplication. So we'll bring down the 15, and then we'll multiply. So I want to come down here and kind of help me out here just to make sure I do this right. So that reduces with that. 2 times 3 is 6. So this is 6, and then I add. So now I have 2/5 times 5. Well, those reduce, that's going to give me a 2. 3 and 2 is 5. 2/5 times 5 is again a 2. So I have a remainder of 0. Now I know that there aren't any more rational zeros, because when I saw the graph it only crossed one place. So I have here my quadratic 15x squared plus 5x plus 5. Now, I know this isn't going to factor because if it did, those numbers would be rational or real zeros. So I know that I'm going to get either irrational or imaginary, so I'm going to have to use the quadratic formula. So again, using the quadratic formula, this is my A, this is my B, and this is my C. So the opposite of B plus or minus the square root of b squared minus 4ac, all of that over 2a, that is the quadratic formula. So we're going to go ahead and substitute these values in. So the opposite of b plus or minus square root of b squared minus 4 times a times c, all of that over 2a. So b is 5, b squared minus 4 times a times c, all of that over 2a. All right, I'm going to have to scroll up here so we can simplify this. Just one step too far. All right, let's go right here. All right, so then we can simplify. So we have the opposite of 5 plus or minus 5 squared. I put 5 squared squared though. That shouldn't be there. You know that. So thanks for catching that. Minus 25. So I have 4 times 5 is 20, and 20 times 5 is negative 300 over 2 times 5 is 30. 2 times 15, excuse me, is 30. So then I'm going to split this into its two fractions, negative 5 over 30. Plus or minus, this will be the square root of negative 275 over 30. So this negative sign here, or this reduces to 1/6. So I have negative 1/6 plus or minus, and now I need to simplify this. So the negative sign is going to become an I outside, 275. So I simply need to simplify 275. So let's see, this is going to divide by, won't divide by 3, so let's do 5. Let's see, that's 25, 25 is 5, so we're going to do 5. That will be 11, and 11 is 1. So the two 5's become a 5 outside, so I have I, 5i, square root of 11 over 30. Okay. Okay, and then because this 5 is outside, I can reduce that, so I end up with I square root of 11 over 6. So I have negative 1/6 plus or minus I square root of 11 over 6. So along with the original 2/5 that I have as a rational zero and these two imaginary zeros, negative 1/6 plus I squared root of 11 over 6 and negative 1/6 minus I squared root of 11 over 6, I have 3 zeros, which if I go back to the top, it says I should have. I can have one real number as a zero, or I can only have one real zero, which is what I have, so that makes sense. And the rational zero came from my list, so that makes sense. So my answer makes sense in terms of what I thought should happen when I began this whole process. All right, so that's a couple of examples. You can rewatch those as many times as you need, but again, it's just a reminder, making sure that we follow these 5 steps. We use the different theorems. We just need to make sure that we follow the 5 steps. We get an idea of where we should go using the fundamental theorem of algebra. We begin by finding the rational zeros. We can use our graphing calculator to help us with our list. We then need to divide synthetically to confirm and identify the rational zeros, creating our quadratic, which then allows us to find the final pair of roots for the expression, and then we have the opportunity then to go back and check and make sure our answer makes sense when we get to the end.